So our talk is about beyond Linux kernel testing, the approaches and challenges. So I'm Shung-Hsi Yu, and this is Yunseong Kim. Yunseong was from Debian mainly on kernel security, and I work for SUSE as a kernel engineer on eBPF, and I'm based in Taiwan. So for our talk, the planned agenda is to give a plain introduction of existing testing and talk about their problems along with the approaches that have been done. And then the next frontier, as well as giving a big picture and ends with a conclusion. So let me get started. So as you can imagine, like Linux kernel has been there a long time. So testing have been quite manual for the majority of its testing in the early days. People run the Linux kernel and see if it works. If it works, then good. If it doesn't, there's some bug, then you have to go to fix it. But of course, that doesn't scale as the Linux kernel becomes more and more complex, and also when it becomes more important. So then there's some automated tools that are used. And there's actually a lot of them. I couldn't cover all of them here, but there's just kind of some examples. And with all those tools, one thing I want to start with is try to categorize them. This is not a formal categorization, but mainly I would separate them into pre-build, build, and executing and running, executable and running by what phase they run the test in. So in the pre-build phase, it's more like working with the source code. You have something like very textual, like you can use grep that just use regex to find some bugs. And you have more higher level that is like clang tidy, which knows the C syntax, so it can do some syntax checking. And on an even higher level, we have more semantic tool. Those are like sparse and smatch and RT-log scope. It knows the C syntax, but even on a higher level, it knows some structure that are used by Linux kernel. For example, it knows what lock is and what you can or cannot do with locks. And on the build level, it's further down. So you have tool like object tool, which is part of the Linux kernel source code. It does check on the compiled object. So when you have native machine code, but it's not linked together yet. And finally, let me just skip one phase and let's go directly to a running phase. So this is actually the test that most of us will be more familiar with. K-unit is for doing unit tests, and K-self-test is more like a functional test. And then we have the Linux test project that is, in a sense, more like an end-to-end test. So a plain way to separate them is to look at them as dynamic tests or static tests. So dynamic tests are running when the Linux kernel itself is running as native code on the machine CPU. And before that, we call them generally static tests. And in terms of runtime cost, the way we separate them is that because the farther you go onto the right when the Linux kernel itself is actually running, the higher the cost is. Like you need more CPU electricity and memory. And the further we go on left, the cheaper it is. So when we plug all the kind of tool I mentioned here, it's not surprising that a lot of tools are on the left side. It's cheap to run, so we can run it often. And run it often means that we catch bug earlier and when the developers still remember what he was trying to do, so it's easier to fix the bug. So that's why we have a lot of tool in the pre-build phase, but we actually have kind of a bimodal distribution. So on the right, you actually still see a lot of tests, the traditional tests. And why do we still have this test if it's like more expensive to run? So the first answer is, of course, it's just like the natural way to testing. Like when you run a software, you try to test it. The natural thing is to write unit tests and functional tests, end-to-end tests. But for Linux kernel, it's actually a different, well, I would say it's the majority reason is that it has less false positive. So by false positive, I mean that when the tool runs and it fails, you assume there's a bug. But maybe there's not actual bug. Maybe there's something wrong with the test. Anyway, there's no actual bug happening, but your test fails. So this is a problem. So for example, if I run my test and it fails and I report it to the upstream Linux kernel developer, so the maintainer will look at it and try to decide that maybe this isn't really a bug because what you mentioned doesn't really happen. Well, or maybe they decide that it actually happened, which is good, then it's actually a bug. But the problem with this is the maintainer have to spend time looking into your report and decide if it's actually a bug. And this this takes a lot of the maintainer's time. And the maintainer time is actually the most precious resource we have in the Linux kernel community. So we try very, very hard to save their time to make sure they have more time to pour into fixing bug and doing other important things. And with all these tests, there's problems, of course. The first problem, well, the major problem, is that it just catches too little bugs. And the root cause of this is just kind of depressing. We have infinite complexity. So Linux runs on your smartphone, on your servers, even on the Land Rovers that went to Mars. So we have to run on a lot of different hardware platforms that are different. At the same time, we have like 12,000 kernel configuration that can be toggled on and off. And we also have a very large code base that is evolving each minute. So we have like infinite complexity. At the same time, we only have finite tests. And furthermore, to make sure that we don't waste the maintainer's time, we try to avoid false positive. And in the trade-off, we kind of have to ignore something that may be a bug. And with all these uncaught bugs, there could be problem because Linux kernel is running a very high privilege. So when you have something like a use effort free bug, the attacker may be able to turn a use effort free into privilege escalation. And essentially, they could become real-day bug that cause company to lose a lot of money. So the way the approach toward this existing problem is in two parts. First, we try to increase the state exploration. By that, I mean like instead of writing tests in like manually case by case, we can use generated tests. So this way, we can explore more of the state input and can explore like possible edge cases that are not detected by the traditional test. So increasing state exploration is just part of the solution. The second part is to also try to increase the catch rate. And by catch rate, this can be done by checking for some sort of behavior or property. I'll talk about it more. But basically, it's come up with some high-level definition of what is a bug or what is a correct behavior. So the actual approach looks more like follow. So before I said you test for property instead of a hard-coded case. So property is just a vague way to say that you check for some general rule. For example, you have a test that checks 1 + 1 = 2. You can come up with a more general statement that basically just say, well, check that n + n = 2n. And it's usually quite obvious after the fact. Like, for example, for Linux kernel, we check something like this. If you're trying to read the memory, then make sure it's initialized. And we come up with a lot more rule for this. Something like null pointer, the reference, a bug, use effort free, a bug. Uninitialized data, also like data race, or more kernel specific, which Yunseong will talk about more, is like sleeping in atomic context. So we have this property, and then we can come up with corresponding checks. Checks for invalid memory usage, you have Kasan, or the kernel address sanitizer. For the data race, it's a kernel concurrency sanitizer, and undefined behavior, even though it doesn't have a K, but it's UBSAN. So with property-based checking or testing, we can already increase the catch rate. So one thing we could start with is to just build kernel with those kernel address sanitizer and just do their own thing, like user just test it their own way, or run these traditional tests like KUnit or key self-tests. But that increased the catch rate, but that alone is not enough. So for the next section, I'll hand over to Yunseong to talk about more and also present some challenges he met.
Thank you, Shung-Hsi. There is always limitation when the contributor sometimes didn't load up test cases. Sometimes finding with kernel coverage help this when there's some omitting from test case. So and even further. So we can equip generator with the code coverage knowledge. So I've been using fuzz testing a few years ago. Fuzz testing, an automated technique that feeds invalid or random input to program. The modern fuzzing, including some coverage guided, structure aware, something like that. So tools like SUSE color and buzzer extended this for kernel and eBPF fuzzing. SUSE color is coverage guide and aware of system calls and kernel structure. Buzzer is aware of both the syntax and semantics of the eBPF programs. So, finding bug with SUSE color on print.rt kernel. This is my recent kernel contribution. So, a brief introduction to print.rt kernel. Print.rt config enables hard real-time performance by making almost all kernel paths printable. It replaces spin locks with RT mutexes and thread interrupts, even allowing some GFP atomic allocation on the kmalloc. Going to be sleep. Yes, that's a fun point. GFP atomic go to sleep. Yeah. Only a few special types of spin locks, such as those prefixes with low on the bar, will not sleep. In print.rt, spin locks may sleep, so they must not be used in print or IRQ disabled sections, nor GFP atomic or no wait flag in the allocation with the kmalloc. So non-print.rt doesn't matter. This is safe, but the print.rt risky. While fuzzing the print.rt kernel after each upstream merged at last year LPC 2024, I hit a sleeping function called from invalid context bug. Even this year, the same issue reappeared. So I'm doing actively showing that some paths still misuse sleeping locks in IRQ disabled context. So as you can see, this core stack same as last year. So I want to fuzzing print.rt kernel. So this print message comes from the config debug atomic sleep, which once when a sleeping function runs in an invalid context in print.rt, it occurs when interrupts are disabled with local IRQ save during KCOB coverage collection that uses spin lock. When starting KCOB in software IRQ context, interrupts are disabled to prevent hard IRQ nesting, but the RT spin lock call within KCOB remote start USB attempts to sleep in IRQ disabled state, so bug occurs. This frequently triggered without the fuzzing in the print.rt kernel. So print.rt maintainer Sebastian and I submitting the patch fixes the print.rt KCOB issue by removing interrupt disabling in KCOB remote start on software context and adding a check to start KCOB only when not in hard IRQ context. As you can see, not in hard IRQ. Removing interrupt disabling allows safe calls to sleeping locks, so bug fix. So as you can see, there's no sleeping in invalid context. In print.rt, spin lock can sleep like a mutex, as I mentioned, so disabling a local interrupt while holding it can trigger invalid context bugs. So nowadays, this code pattern should be avoided. You can see local IRQ save after spin lock. So the issue that nearly all Linux kernel device driver books from a few years ago still recommend this pattern as it good practice. Yeah, we must use this pattern on the right side. So the patch below fixes USB dummy H locking and other things for similar print sleep error. An anti-pattern where local IXAP is used before the spin lock, it can be detected using regex that Shung-Hsi mentioned with the grep plus regex or some cautionary static check. The patch fixes it by switching to spin lock IRQ on the subsystem. Yeah, RAID 5 subsystem. And this is some similar, but when using the bit spin lock, they disable the preemption. So after the bit spin lock, using spin lock also makes some bug sleeping function called from invalid context. So this pattern should be fixed. So I reported it on the GFS2. Overall, while these static checks are valuable for preemptively finding direct and some indirectly sleeping atomic bugs, how we can imagine for this condition, for some adding condition for the preempt disable and schedule with the sleeping function. So it is hard. Static checks have a limitation for this check. So we need a different approach. The method that follows offers a solution from a perspective different than the traditional one. This alternative approach asks, instead of finding bugs, how about proving their absence? Property verification focuses on defining correct behavior rather than finding bugs. For example, a process must be in one of 4 stages: running, runnable, sleeping, zombie, or stopped. And transitions between them follows defined rules. So instead of searching for bugs, property-based approach defines correct behavior, like eBPF verifier and Linux-kernel Memory Model. So including formal and runtime verification to ensure correctness. Asks whether the system is built correctly, whether it conforms to each specification. The specification is the key point. Tools like Agni for eBPF verifier and Litmus for LKMM by the Paul McKinney provide probable guarantees of correctness. So runtime verification, this is the recent features that merged upstream, helps monitor potential violations such as sleeping in atomic context in the Linux kernel. We can define the allowed stage for a task, not in atomic context, and interrupt enable in atomic context but not calling RT sleepers, and interrupt disable but not calling RT sleepers. So using linear temporal logic called LTL, we can formally express this as a rule with some coding in the kernel module for RV. So allowing the kernel to detect violations at runtime from our definition from the LTL, while preserving real-time constraint. So I will hand over Shung-Hsi again, give presentation.
So with Yunseong presenting so many different more approach and challenge he made, I want to make sure that we have kind of a bigger picture. Basically, take a step back and look at all the tools that we have mentioned so far. So as before, I try to separate them into pre-built, build, executable, and running. So if we try to fill in all the tools that we have met so far, it kind of can be categorized into this. So on the right side, again, we have the dynamic tests that are more costly to run. On the left, it's the static tests that it's more cheaper to run. But on the top, we have tools that are mostly trying to prove that there exists a bug, there is a bug to be fixed. On the bottom side, it's a tool that is actually more like verification. So it tries to prove that the behavior is correct. So on the top right, it's those tools that we're more familiar with, like unit tests, function tests. It runs dynamically and tries to prove that, oh, something is wrong. And on the top left, it's the more traditional static tools that we have. Like it looks at the source code and tries to say, oh, this thing is wrong. But because we want to avoid the false positive, we end up being kind of more conservative. So a lot of tools cannot, will try to limit their approach and don't cause too much waste time. And on the lower left, it's actually more like those formal verification tools, the static analysis tool that tries to look at the code and decide that, oh, the behavior is correct. But they're also quite prone to false positive because you're not actually running code. And the interesting kind of like the new region is on the lower right, which is runtime verification. So the tests are, or the Linux kernel is actually running, so you have less chance of false positive. But at the same time, it's also trying to prove that the behavior is correct. So you still have maintained quite a good catch rate. And I think that's an interesting new work region. And to take a even further step back, so I think the bigger question is to ask, like, what do we actually want in the Linux kernel testing and testing in general? We want accurate tests, which basically translates to you want tests that are highly precise. So when the test fails, you want to be very sure that there's an actual bug. At the same time, we also want to have high recall. So when the test pass, you want to be pretty sure that, so I shouldn't have any bugs in my code. But at the same time, we want to be pragmatic. So if you want to spend forever to come up with the best like testing method, that you can do that, but it won't help the community so much. So in the end, I think we don't really have a silver bullet that is like easy to come up with and correctly catches all the code, but also don't miss anything. But I think runtime verification may be stepping into an interesting category that is like less likely for false positive, but enough catch rate and also quite easy to write by the syntax that Yunseong has shown. So that is the end of our talk. I hope that's interesting. And please consider contributing to Linux kernel testing. Like there could always be more contributor working on that, and come to talk with us after the entire day. Thank you.
Thank you.
Thanks for a wonderful talk. I have a philosophical question to you. So you described those wonderful tools, runtime, the dynamic analysis, static analysis, fuzzing. Do you believe that sometime in future we will cope with all bugs? And those tools, maybe AI-powered tools, testing, will help us to get rid of all of the bugs. Is it really possible to get into it?
Okay, I think that sounds like an interesting like interview question. So maybe I should say like it depends. But I think there's definitely, I personally see a lot of possibility with AI integrating with formal verification tools, because formal verification tool is very powerful, but traditionally require a lot of knowledge that is both knowledge of verification but knowledge of kernel. And I think with AI, we may be able to shorten that gap to some degree that may be quite impactful.
And right now, you see how bugs are introduced, then tested, then found, fixed, and tested, right? And where is the bottleneck in this process? So the fixing or writing the tests, what is the most slow part, would you say?
Shung-Hsi mentioned that the maintainer's time is most precious, and there is some bottleneck for the maintainer, and the code merged from the maintainer's review. So I think that point would be a bottleneck for the all procedure, and there is needs some more people to code review and testing it. So I think that activity, the precious for the Linux kernel maintaining.
So that is the part which is not easily solvable with AI and so on, right?
Yeah, I think AI have a limitation for the some reviewing all the kernel context, because as you know, Linux kernels have some tricky implementation for their some great performance and some other things. So I think AI need more time for all those things. And recently I fixed some bug, but this bug make other bugs. There is something there is some issue, something like that. So I think merging from the code from the written by the AI and maybe have more consideration in this time. Maybe future, yeah.
Thanks a lot for your answers. Thanks.